In this study, we examine a class of rearrangement problems where items to be sorted are stored in a lattice-like storage. The setting frequently appears in our daily lives, for example, arranging shoe displays at stores, the seasonal adjustment of a shoe collection, organizing a wine cellar, or alphabetizing books on bookshelves. In rearranging the items, we assume a pick-and-swap model, where the robot may pick up or drop off items, move around, and make item swaps. For such problems, a plan P may be fully specified as a sequence of end-effector locations P0 through Pn plus 1, where P0 is the end-effector rest position, usually at the top left of a lattice. We would like to seek a plan that minimizes the time it takes to solve a rearrangement problem, where each pick and swap has a cost Cp, and end-effector travel has a unit distance cost of Ct. The optimization is performed sequentially. Under the setup, we examine 4 settings in detail: labeled one-dimensional problem LOR, partially labeled one-dimensional problem POR, labeled two-dimensional problem LTR, and partially labeled two-dimensional problem PTR. We briefly highlight our algorithmic results with provable guarantees. For LOR, we may minimize the number of pick and swaps using cycle following. For this example, we first follow the cycle 3-4-1, which uses 4 pick and swaps. This solves the problem for items 1, 3, and 4. For the 2 cycles, 3-4-1 and 9-8-5-7-2, a total of 10 pick and swaps is needed. We then further minimize the end-effector travel. We observe that following cycles one by one may incur additional end-effector travel. In this example, following the cycle 4-1 and then 5-3 incurs a distance of 14. If we switch in the middle, we can actually save 4 units of distance without adding more pick and swaps. Together, cycle following and cycle switching yields an optimal algorithm for LOR. For the partially labeled setting POR, we will again solve it by cycle following. However, because an item does not have a unique destination now, the cycles are not unique. Here, we first perform a matching, which induces a set of cycles. These cycles can be merged to reduce the number of pick and swaps. The first type of merging does not add more distance cost. The second type does. The additional distance incurred in this manner can be minimized by computing a minimum spanning tree over all affected cycles. Combining cycle following, cycle switching, and cycle merging yields an optimal algorithm for POR. Moving to the 2D setting, we can show that minimizing the end-effector travel is in fact NP-hard. Nevertheless, we can show that greedy cycle following can still do very well because the number of cycles in a random permutation is quite small. This fact is exploited elsewhere, for example in Trelevan's work on pickup and delivery problems. It was also publicized in the 100 prisoners problem. Because travel within a cycle has fixed cost, and travel between cycles can be ignored, a cycle following algorithm is asymptotically optimal. We can further improve the algorithm for LTR by adding cycle switching. For example, we can use cycle switching to shortcut this cycle following solution to reduce end-effector travel cost. This leads to improved optimality when the number of items is small. Similar computational results hold for the partially labeled case. Simulation results further confirm the efficiency of our algorithmic solutions. In general, we observe that our optimal or optimized solutions provide a sizable improvement in terms of optimality. To conclude, we proposed the lattice rearrangement problem and the pick and swap model, studied the structural properties of many variations, and developed high-performance algorithms for all. Our results generalize to higher dimensions.